Well, halo guys. Jadi hari ini adalah hari ketujuh dan minggu pertama dari MITxTPB Challenge. So I think I gonna make the lecture. Wait. Oh, nggak bisa. Ya, jadi hari ini hari ketujuh. Seharusnya aku udah menyelesaikan fisika, problem set fisika dan matematika dari 1 sampai 3. Jadi kalau kita lihat di lecture di silabusnya, seharusnya aku udah selesaikan bab problem set 1 2 di minggu kedua dan minggu ketiga di minggu ini. Tapi karena kemarin telat mulai, jadi terpaksa molor, dan hari ini aku pengen ngejar problem set 1 sampai 3. Jadi kita akan live sebisa mungkin pada sesi kita dapat Pomodoro 8. Jadi sekitar 8 jam bekerja dan 40 menit 40 menit istirahat. Jadi karena nanti akan ada istirahat panjang di maghrib di jam 6, jadi sekitar 1 jam. Jadi kita kurang lebih live 10 jam lah kita usahakan, dan harus selesai problem set 1 sampai 3. Itu goals hari ini. Dan kalau sempat ntar malam skimming sebelum tidur, baca skimming tentang single variable kalkulus untuk hari Senin, untuk besok. Karena seharusnya juga seperti tadi, matematika itu harusnya sudah selesai. Jadi kalau kita lihat di 1801 SC, nah aku kan pakai yang SC ya. Perbedaan yang SC, kelas SC sama kelas yang non SC. Jadi ini ada 1801 SC, 1801 aja. Nggak nampak ya? Nggak nampak ya? Bentar. Mana sih? Cek. Nampak kan? Nampak kan? Jadi ada 1801 SC dan 1801 nggak SC. Perbedaannya adalah yang SC ini didesain untuk orang yang ingin belajar secara mandiri dan biasanya lebih lengkap. Kalau yang non SC ini non SC, course matematika non SC, dia ya kurang lengkap. Nggak kurang lengkap juga sih, nggak tahu karena aku belum selesaikan. Dia tapi rata-rata yang kelas di SC itu ngambil videonya ya punya non SC. Nah ini cuman dipotong-potong gitu, jadinya terlalu banyak video. Kalau yang SC, jadinya aku di matematika itu pakai 2 sumber. Untuk video lecture aku pakai yang non SC, untuk exam ataupun problem set mungkin aku juga akan pakai yang di SC, jadi combine. Jadi besok targetnya menyelesaikan punya minggu ini, yaitu lecture 1, lecture 2, lecture 3, lecture 4, lecture 5, lecture 6, dan sampai besok mengerjakan examnya. Jadi kita lihat apakah besok bisa sesuai target, yaitu untuk membayar hutang punya minggu pertama untuk yang matematika. Jadi kita hari ini akan melakukan fisika aja. Nah kan, jadi dia dipotong-potong gitu. Jadi ini punya lecture-nya yang non SC. Kalau yang non SC sekali lecture langsung 1 jam gitu, 50 menit ya kan. Kalau yang non SC dia dipotong-potong gitu, ini yang 7 menit aja, 11 menit aja. Terus ada tambahannya lagi juga, terus ada tambahannya dari bapak ini, jadi banyak banget yang harus dilihat video. Jadi kita coba dulu tes untuk mengikuti lecture-nya yang ini. Kita reading apa yang dia suruh. Ini readingnya guys, ini reading yang dia suruh. Oh enggak sih, aku baca yang lecture note ini. Jadi dia ada kasih lecture note, udah aku print juga semua itu. Jadi ini adalah hal-hal yang akan dibahas di lecture-nya si bapak ini, si bapak-bapak ini, yaitu Profesor David Jarrison. Seperti itu. Jadi nanti malam kita akan coba reading lecture note-nya, skimming, yaitu ini kah? Ini sesi 1. Udah di print sih. Oke, untuk matematika udah selesai. Besok kita ngambisnya. Untuk fisika hari ini kita semalam aku udah skimming semua chapter reading yang disuruh. Ada 9 chapter ini yang kalian lihat. Dan ini akan dibahas di lecture-nya si fisik aku pakai yang SC 801 SC. Ini ada week 1, ini semua untuk week 1 tentang one dimension kinematics. Untuk vektor, kalau untuk vektor dia wajibkan untuk di review sebelum kita memulai course dia. Aku udah nge-review. Ini ada bacaan untuk week pertama, chapter 4 one dimensional kinematics sama dimensional kinematics. Aku belum terlalu dapat detailnya, tapi untuk idea, general idenya, ide yang umumnya aku udah dapat dan aku tulis merah di pulpen merah ini. Ini tentang bab ini belajar apa sih secara general, dan ini aku tulis ketika aku udah skimming semalam. Jadi kita lihat, jadi ketika kita melihat lecture, pedomannya juga tetap ini. Jadi ketika mungkin di lecture nggak jelas, jadi aku baca ini. Kalau mungkin juga belum jelas, aku coba langsung terjun ke problem setnya dan coba memetakan bab apa ataupun subbab apa yang belum jelas, sehingga aku bisa langsung ngelihat detail di readingnya. Jadi ya itulah intinya sih, secepat mungkin mengerjakan problem set. So like that. Itulah. Mulai jam 1 aja lah. Masih ada 10 menit lagi. Mungkin cerita-cerita aja sih. Untuk fisika di MIT ini susah sih. Maksudnya sangat challenging, menantang. Karena apa? Karena banyak konsep matematikanya. Bukan konsep matematika sih, lebih ke konsep fisika yang dibahas secara matematika. Jadi memang benar-benar harus kuat matematika sih untuk bisa tahu lebih dalam konsep tentang fisikanya. Oh ya, dan juga di sini aku pakai 2 sumber untuk fisika. Kenapa? Karena setelah aku baca-baca yang di ini yang di lecture SC ini terlalu yang kayak tadi terlalu berbasis matematika, sehingga mungkin konsep-konsepnya itu lebih kuat tetapi aplikasi fisikanya mungkin kurang terlalu ditekankan, kurang dapat. Jadi aku dapat satu lecture dari Walter Lewin, ini salah satu profesor di MIT. dia terkenal kalau kalian lihat yang ini yang dia ada yang dia naik bola kayak gitu. Jadi dia sering kasih demonstrasi ketika dia ngajar di MIT, terutama dia ngajar di ini 801 fisika dasar. Dia sering menggunakan demonstrasi, misalkan kayak ada aja yang dia bawa kayak ini nih.
Today we're going to talk about spring.
Mana sih yang dia naik?
Nerve-wracking. Where are we now?
Ada kok.
7.
Ini dia. Jadi dia sampai naik gini, guys. Saking demonstrasinya, saking demonstrannya. Apaan sih demonstran? Jadi aku akan juga ngelihat lecture-nya dia, tapi ada tapinya, lecture-nya dia juga nggak semudah yang kita bayangkan. Untuk memahami aplikasi-aplikasi fisika ini, dia juga bahasnya pakai konsep matematika fisika. Jadi ya kalau kita cuma lihat lecture dia, kita nggak akan ngerti apa yang dia bahas. Jadi ya aku akan lihat lecture ini sebagai tambahan aja dari lecture yang ini. So like that.
analysis of motion. And we'll start with one-dimensional motion. Let's just consider a person running along a road. And so here's our runner, and here's our road. And what we want to do is be able to describe the position, the velocity, the acceleration of this runner. In order to do that, we need our first mathematical tool. The first thing that we want to choose is an origin. We can pick the origin anywhere we want. That's a degree of freedom. So let's choose a point along our road as our origin. The next thing to do is to choose an axis. Well, the road is naturally defining an axis for our problem, and so we'll call this the x-axis. Now, along with that axis, we want to divide that up into some type of units. So we might divide our axis like this. And what's important here is to introduce a positive coordinate direction. And so the way I'll do that is I'll call this the plus x, and on this side of the origin, x is negative. Now, the third most important thing is that we're going to talk about vectors in physics. So we want a choice of unit vector. Now, because it's only one dimension,
There's an important distinction to make between cause and effect when analyzing the motion of objects. There are two very separate questions that we can ask. The first is, how does a particular object move? This is a purely descriptive.
iTunes-nya nggak nampak. Kok bisa ya? Kita lihat sistem preference. Screen recordings. Aku nggak ada, astaga. pertanyaan ada. Oke, sudah baik.
We now like to begin our analysis of motion, and we'll start with one-dimensional motion. Let's just consider a person running along a road. And so here's our runner, and here's our road. And what we want to do is be able to describe the position, the velocity, the acceleration of this runner. In order to do that, we need our first mathematical tool, which is a coordinate system. What is a coordinate system? Well, the first thing that we want to choose is an origin. We can pick the origin anywhere we want. That's a degree of freedom. So let's choose a point along our road as our origin. The next thing to do is to choose an axis. Well, the road is naturally defining an axis for our problem, and so we'll call this the x-axis. Now, along with that axis, we want to divide that up into some type of units. So we might divide our axis like this. And what's important here is to introduce a positive coordinate direction. And so the way I'll do that is I'll call this the plus x, and on this side of the origin, x is negative. Now, the third most important thing is that we're going to talk about vectors in physics. So we want a choice of unit vector. Now, because it's only one-dimensional motion, we only need one unit vector. So what that means is a choice of a unit vector at every point. Let's just consider a point here, P1. So our unit vector, I'll call it I hat 1. Now let's pick another point. We'll call this the point P2, and over here, we'll choose a unit vector, I hat 2. So every single point in space has a unit vector. Now, what's unique about this one-dimensional linear Cartesian coordinate system is the following. These unit vectors have the same magnitude. A unit vector, by definition, has magnitude 1, and they're pointing in the same direction. So if two vectors have the same magnitude and point in the same direction, they're equal. So what makes this coordinate system unique, this Cartesian? So our unit vector, I'll call it I hat 1. Now let's pick another point here. We'll call this the point P2. And over here, we'll choose a unit vector, I hat 2. So every single point in space has a unit vector. Now what's unique about this one-dimensional linear Cartesian coordinate system is the following. These unit vectors have the same magnitude. A unit vector, by definition, has magnitude 1. And they're pointing in the same direction. So if two vectors have the same magnitude and point in the same direction, they're equal. So what makes this coordinate system unique, this Cartesian coordinate system, that at every single point, no matter where we are, the unit vectors point in the positive direction. Because they have the same magnitude and direction, all of these unit vectors are equal, and we call that I hat. So symbolically, we may draw a picture and indicate our unit vector in the positive x direction. And this is our coordinate system, and we can next begin to describe the position and the velocity of our object as it's moving along this x direction. Now that we've chosen a coordinate system for our runner going along a road, we now want to describe the position function of that coordinate system with respect to our choice of origin. Now, the runner is a non-rigid object. Legs and arms are moving back and forth. So let's just imagine that there's some fixed point in the runner at the center. And then let's give a vector. So we're going to draw a vector from above our origin to that point. And this is what we'll refer to as our position function. Now remember, every point here has an x coordinate. So we can now introduce our position function, which we'll call x of t, which is the coordinate location with respect to the origin. This is a function that will change in time. And our position vector is r of t equals the position function x of t. Now remember, this is a vector. The position function is just a quantity that's describing the location of this point with respect to the origin, but the unit vector is how we describe this as a vector, and so we write I hat. Now, x of t is what we call the component of the position vector. Remember, a vector has a component and a direction, and the component is the position function, and that component, x of t, can be positive, as you see in this particular case. X of t can also be 0. That's if you're located at the origin. And if our runner is on the other side of the origin, x of t can be negative. So the component of the vector, of the position vector, can be positive, 0, or negative, and the direction of the position vector is the sign of the component times I hat. If the component is negative, then we have a negative I hat. The position vector is pointing backwards in the minus x direction. And if x of t is positive, positive I hat, position vector, as shown in this particular case, is in the positive I hat direction. So that's our first vector, the position vector in one-dimensional motion. Now, we've described the position vector of the runner. Let's try to describe what happens in time as the runner moves along our road. Suppose at a later time, our runner has gone down the road just a little bit, and so runner has moved a little bit. Remember, at time t, we described the position vector, r of t, was equal to the coordinate function, x is a function of time, I hat, and this distance here was our x of t. Now, our position vector, a little bit later, so here we're at time t plus delta t, the runner has moved a little bit, and we'll now describe the position vector, because I don't want to overlap it, that center point is up here, it's going to point in this direction, and this is what we call r of t plus delta t. And that vector, r of t plus delta t, the coordinate function is no longer at time t, but t plus delta t, I hat. And we would now like to describe the displacement vector. So our next step is to describe the displacement vector.
But because it's work on T, so we don't have T.
The interval t to t plus delta t. And that displacement vector is defined, we use the symbol delta r, and what we mean is the vector r of t plus delta t minus the vector r of t. Now what that vector corresponds to is the vector right here. This is our delta r. And if we now use our two definitions here, then this becomes x of t plus delta t minus x of t I hat. And this quantity here we refer to as the component of the displacement vector. So delta x is the component of the displacement vector. And as before, the component can be positive, which would correspond to the person moving a positive component, positive I hat direction, in the positive x direction, as shown in this figure. If the displacement vector is 0, the person could have run forward and come back, and at time t plus delta t be in exactly the same spot as time t. The displacement vector is 0 in that case. The displacement vector could have a component that's negative, and what negative means is at the end of this interval, t plus delta t, that the person is on to the left of the runner. And so this quantity would be negative. And so this is our crucial displacement vector that describes only the difference in positions between the person between time t plus delta t and time t. Now that we've described the displacement of our object, remember that our displacement vector, delta r, in this time interval was x of t plus t minus x of t I hat, which we denoted as delta x I hat. Now let's just remind ourselves that this distance here, that's delta x, and this whole distance from here over to there, that's what we mean by x of t plus delta t. And now what we'd like to do is describe what we call average velocity. And our average velocity depends on our time interval. So this is for the time interval, t to t plus delta t, while the person has displaced a certain amount of under delta r. And our definition for v average, it's a vector quantity, so we'll write v average. We'll use 3 bars to indicate a definition. It is the displacement during a time interval delta t. So as a vector, we have delta x over delta t I hat. And this component here is what we call the component of the average velocity. So this is the component of the average velocity. And again, as before, this component can be positive, 0, or negative, depending on the sign of delta x. And the key point here is that average velocity depends on whatever time interval you're referring to. So that's our definition of average velocity. And now what we want to do is consider what happens in the limit as delta t becomes smaller and smaller and smaller. And that will enable us to introduce our concept of instantaneous velocity. What we'd like to do is explore how you differentiate position functions to get velocity functions to get acceleration functions. So what we're going to consider is a rocket. So I'm going to choose coordinate system y, and here's my rocket, and I have function y of t, and I'll have a j-hat direction, but this will be a one-dimensional motion. Now, I want to express, while the rocket is thrusting upwards and the engine is burning, we can describe a function y of t to be equal to 1/2 a constant a naught minus the gravitational acceleration times t squared, and we're going to have a separate term. Here, which is minus 1 over 30, and you'll see where this 30 comes in as we start to differentiate. Same constant a naught t to the 6th over t naught to the 4th. Now in this expression, a naught is bigger than g, walking motion, that has a non-uniform acceleration. What we'd like to do is explore how do you differentiate position functions to get velocity functions to get acceleration function. So what we're going to consider is a rocket. So I'm going to choose a coordinate system y, and here's my rocket, and I have a function y of t, and I'll have a j-hat direction, but this will be a one-dimensional motion. Now, I want to express, while the rocket is thrusting upwards and the engine is burning, we can describe a function y of t to be equal to 1/2 a constant a naught minus the gravitational acceleration times t squared. And we're going to have a separate term here, which is minus 1 over 30. And you'll see where this 30 comes in as we start to differentiate. Same constant a naught t to the 6th over t naught to the 4th. Now, in this expression, a naught is bigger than g. And also, this is only true, this holds for the time interval 0, less than or equal to t, less than t naught. And at time t equals to t naught, the engine shuts off. And at that moment, our expectation will be that the y component of the acceleration should just be minus g for t greater than t naught. So now let's calculate the acceleration as the velocity and the position as functions of time. So the velocity, in each case, we're going to use the polynomial rule. So the y component of the velocity is just the different derivative of t squared, which is just 2t. And so we get a naught minus g times t. And when we differentiate t to the 6th, the 6 over 30 gives us a factor 1 over 5. So we have minus 1 over 5 times a naught t to the 5th over t naught to the 4th. And this is a combination of a linear term and a term that is decreasing by this t to the 5th factor. And finally, we now take the next derivative, a y of t, which is d dy dt. I'll just keep functions of t, but we don't really need that. And when we differentiate here, we get a naught minus g. Now you see the 5s are canceling, and we have minus a naught t to the 4th over t naught to the 4th. Now, at time t equals t naught, what do we have? Well, ay at t equals t naught. This is just a factor of minus a naught, those cancel, and we get minus g, which is what we expected. And a term that is decreasing by this t to the 5th factor. And finally, we now take the next derivative, a y of t, which is d dy dt. I'll just keep functions of t, but we don't. Need that. And when we differentiate here, we get a naught minus g. Now you see the 5s are canceling, and we have minus a naught t to the 4th over t naught to the 4th. Now, at time t equals t naught, what do we? have, well, ay at t equals t naught. This is just a factor of minus a naught. Those cancel, and we get minus g is what we expected. Now that we've described the instantaneous velocity of an object, we'd now like to describe what its acceleration is. Velocity and acceleration are complicated things. One of the reasons why acceleration is such an abstract quantity is, for example, if I take this marker that's in my hand and I throw it up in the air and I catch it, you can see with your eye velocity. You can see the speed, you have a sense for it, you can see it change its direction. So velocity is something that as a human being with our eye as a mechanism for determining motion, velocity is a very basic concept. But acceleration is a much harder concept. For instance, when I take that same object and I up that. As it falls down, its velocity is increasing, and so we say it has an acceleration. But is that acceleration a function of time? Or is it constant in time? Is it varying in time? Is it a polynomial? Is it a constant? Those are much harder to see. Again, let's drop this object. So when I drop that object and I catch it down here, our eye does not tell us intuitively anything about the mathematical nature of that acceleration. And that's why acceleration is a much more abstract quantity. In fact, a great question is the following. When I throw this object up in the air, let's focus at its highest point. So I throw it in the air, and it comes down. When the object was at its highest point, was its velocity 0? Was it its acceleration 0 or non-zero? A hint to this question is in Newton's second law, F equals ma. If there's a force acting on this object, there must be an velocity 0. Was it its acceleration 0 or non-zero? A hint to this question is in Newton's second law, F equals ma. If there's a force acting on this object, there must be an acceleration, and that force is the gravitational force. And when this object was at the top of its motion, I didn't turn the Earth off. So there's still a gravitational force. And so for an object in free fall, Now, free fall just is which means under the influence of the gravitational force. We can conclude from Newton's second law that the gravitational force, ma. So this gravitational force is non-zero, and so therefore the acceleration is also non-zero. So once again, as I throw this object up in the air, nobody turned gravity off. We're not in empty space, and near the surface of the Earth, the gravitational force is non-zero. The acceleration
Gravitational force is not zero.
is not zero. So throughout this motion, this object is accelerating. I choose this example to show you that acceleration is a very abstract concept, and now our goal is to figure out how to mathematically define acceleration in terms of our velocity. We've now described what we call the instantaneous velocity at some time t. And we talked about it as a limit, as delta t goes to zero, of the displacement over the time, which we wrote as the derivative of the position function in terms of I hat. Now, this derivative, we're going to use a notation. We'll just write that as v of t I hat, where v of t is the component of the instantaneous velocity at time t. Now remember, this derivative, we're going to use a notation. We'll just write that as v of t I hat, where v of t is the component of the instantaneous velocity at time t. Now, remember, this is just a symbol, but we describe this as the derivative of the position function, which I'll indicate as a function of time. And that's what we mean by the component of the instantaneous velocity. Now what we'd like to do is ask ourselves, how does the velocity change in time if the runner is increasing their velocity? Well, in general, we'll do exactly what we did before. What we'd like to introduce first is the concept of the change in the velocity delta v, which we'll describe as the velocity at time t plus delta t minus the velocity at time t. So what we have in here is the change, the component of the change of that velocity, and this quantity is how the velocity changed in a time interval between t and t plus delta t. Remember, this is very specifically for this time interval. Now what we'd like to do is take the same limiting process. Let's take the limit as delta t goes to zero of this change in velocity over time. So we have the limit as delta t goes to zero of delta v, delta t, I hat, and this quantity is what we call the instantaneous acceleration. Now, at before, what we're doing is we're plotting the component of the velocity as a function of time. Let's just say, again, that we have some unusual function. I'll just draw it like this. And here's the picture at time t. Here's the picture at time t plus delta t. This change, delta v over delta t, this is v at t. Up here, this is what we mean by, let's just, remember we're plotting the velocity as a function of time, v of t plus delta t. And this quantity here, which is delta v over delta t, again, we can even call, as we said before, we can call this average acceleration. But what we're interested in is as we take the limit, as delta t goes to 0, then the slope changes, you can see, and we continue this limiting process until we shrink delta t down to 0, and that what we have here is this is the slope of the tangent line, and that's what we call the instantaneous acceleration. So if we want to use a notation, we don't want to keep on writing limit delta t goes to
Don't want to keep on writing.
So what we can write is a of t. It has a component, a of t, I. And that component,
It's component of t, okay.
a of t, this is precisely the derivative of the velocity function as function.
Oh, I see. So basically we can say that
Of time. And so now we've described the position vector, the velocity vector, and the acceleration vector associated with motion. A function of time. Of t, it has a component, the position vector, and that component, a of t, this is precisely the derivative of the velocity function as a function of time. And so now we've described the position vector, the velocity vector, and the acceleration vector associated with motion. Let's consider a very simple example of a runner in which our position function, x of t, is given as a quadratic function in time. It will be a constant, b times t squared. Here, b is a constant. Now, always important example of a runner in which our position function, x of t, is given as a quadratic function in time. It will be a constant, b times t squared. Here, b is a constant. Now, it's always important in SI units to consider what the units of this constant is. Because the position function is measured in meters and time is measured in seconds, b is a constant and it has units of meters per second squared. And here's an example of a runner, and let's make a plot of that position function. So we're going to plot x of t as a function of time. B here, let's make b a positive constant. And so our function looks something like that. Now, the velocity, component of the velocity, remember v of t is given by dx dt. Of this function. And the derivative of a polynomial t squared is very simple. That's just simply 2b. Now, the velocity, component of the velocity, remember v t, is given by dx dt. Of this function. And the derivative of a polynomial t squared is very simple. That's just simply 2b times t. Again, let's look at our units. Because b has the units of meters per second squared, and we're multiplying that by second, we have the units of velocity in SI units as meters per second. Now, let's plot that function. Notice this is a linear function. And so if I plotted underneath here, the velocity as a function of time, it starts off with a zero slope. Remember, we're looking, our velocity at any given time corresponds to the slope of the tangent line to the position function. And you can see that slope is increasing. Now, you wouldn't know from this graph, if you did plot t squared, it's increasing linearly. It corresponds to the slope of the tangent line to the position function. And you can see that slope is increasing. Now, you wouldn't know from this graph, but if you did plot t squared, it's increasing linearly. And so our velocity function, the initial slope is 0 at t equals 0, and it's increasing linearly in time. So we'll just draw that as some linear function. And the slope here of this function will be now the acceleration. So a of t is the derivative of the component of the velocity function as a function of time. And this derivative is quite easy. It's just simply 2b. Now notice those have the units of meters per second squared, which are our units for acceleration. When we again look at the slope, notice that at every single point, the slope of the velocity as a function of time is a constant. The slope here is just equal to 2b. And so now, if we plotted our acceleration function, we have this point, 2b, and every single point has the same value of acceleration. So here, the acceleration is an example of constant acceleration. And this is our simplest case. Notice we started with the position function, we differentiate to get the component of the velocity and to get the component of the acceleration. So this is a very simple model for a runner who's increasing speed linearly, accelerating at a constant rate.
If we know the position x of t of an object, as a function of time, we can use differentiation to calculate its velocity and its acceleration at later times. Essentially, by taking the derivatives of the position, we know everything there is to know about the motion. Sometimes, however, we'll want to go in the other direction. We'll have the acceleration as a function of time, and we'll define the velocity as a function of time, or the position as a function of time. We'll use a technique called integration, and let's see how that works. To begin with, suppose we have a constant acceleration. So our acceleration a of t is some constant a naught. In that case, we know that this constant acceleration can be written as the change in velocity, delta v, over some time interval, delta t. And therefore that the change in velocity, delta v, over some time interval, delta t, can just be written as a naught, the acceleration, the constant acceleration, times elapsed time, delta t. And we can see this graphically if I plot acceleration versus time. Here's my constant acceleration, a naught. Let's say this is time 0, and here's the time delta t. The change in velocity, a naught times delta t, is just the area of this box. That box being defined by the time interval 0 to delta t, and it's the area under the curve a naught. So if we know the velocity at time 0, and we know the constant acceleration a naught, we can calculate velocity at any later time.
Penampakan.
In this way, because the change in velocity from that initial velocity is given by a naught times delta t. Now let's consider a slightly more complicated example. Suppose the acceleration isn't constant, but is changing linearly.
Ni live ni.
So for a linearly changing acceleration, I can draw this graphically as well. Here's acceleration. This is time equals 0. Suppose the acceleration is just increasing linearly, and I'll call this time delta t.